Hi everyone, Lloyd Rieber here again with my next presentation of the course, Statistics in Education for Mere Mortals. In this presentation, we continue the introduction to the topic of descriptive statistics. Now, up to this point, we've explored and considered some statistics that you have known well, such as the mean, and some that you have at least heard of or have had some familiarity, such as the standard deviation. Now, we are going to explore a statistic that may be completely new to many of you, the z-score, also known as a standard score. But you will see just how incredibly useful z-scores can be and how easy they are to calculate. And we are now beginning to really build on what we've learned so far, a pattern that will continue until the end of the course. This also means that you need to be sure that you fully understand what a z-score is and how it is computed in order to be successful in material that will come later. Believe it or not, we've already done the hard part in computing a z-score, namely computing deviation scores and the standard deviation. Using that work, you'll see that computing a z-score, especially with Excel, is child's play. Okay, let's get started. Okay, you know that I have a lot of animals. Well, here's a picture of Sunny, one of our many dogs we have had over the years. Now, like a lot of dogs we've owned, this one just showed up one day. This is a very familiar story to anyone living out here where I do in rural Georgia. Now, Sunny is a fun-loving young dog with lots of energy, and I hope you could tell this by looking at the photo of him. My wife really thinks he's a bit undisciplined, so let's imagine that I took him to obedience training school. All right, so imagine that I come home at the end of the training, and I proudly tell my wife that Sonny scored a 95 on his final exam. Now that sounds pretty good, doesn't it? And I'm, of course, hoping that the conversation ends there. But no, she asked me a few questions such as, really? How many points were possible? I have to admit that 200 was the maximum number. So I admit to being a little deceptive because it wasn't based on a percent. Now a 95 sounds pretty dismal, but I tell her that 101 was the highest score of the group. Okay, Sunny is rebounding in her respect for him, but then she asks, well, what was the average score? And being the honest guy that I am, I say sheepishly, 98. So now even Sunny starts to whine a little bit off on the side. Then I tell the whole story by saying that Sunny's 95 was actually the lowest of all the dogs. Now, the point of this little piece of fiction is that a score like 95 can only take on meaning when it is compared with the other scores in the group. So rather than give an individual raw score and then go through an explanation of how one can make sense of that or how to compare that score with the rest of the scores of the group, one could give instead a z-score or a standard score. A z-score, or again called a standard score, will show how far an individual's performance is from the mean in standard deviation units. So we're already very familiar with the idea of computing a deviation score, which is a individual's raw score minus the mean. So we understand that, but we're going to then divide that number by the standard deviation, which we've already computed. So, we make conversions to standard units all the time. For example, I think we're all prone to convert things to percentages. So if I were grading projects for 2 courses, I might say, well, I have 6 out of 12 done in one and 9 out of 18 finished in the other. But I could have just said I'm half done, I'm 50% done grading in both of the courses. We just kind of do that naturally. As another example, I live in Madison County, Georgia, in something called the Sanford community. Now, if I say that I live 129 kilometers from downtown Atlanta, you might either thank me for the information, you were then also probably raised outside of the U.S., or you might quickly ask, how many miles is that? Or you might actually just walk away and say, I really should know this, and you would do a conversion in your head, or you'd look it up that you might know that 1 mile equals 1.6 roughly kilometers. And so, if I'm 129 kilometers, that means I'm about 80 miles from downtown Atlanta. Now, converting a raw score to a z-score is similar, except that two statistics are involved in the conversion: the mean and the standard deviation. So let's take a look at the formula. So just as I described, a z-score is equal to the deviation score, which is again the raw score minus the mean, and we're going to divide all that by the standard deviation. So by doing that division by the standard deviation, we're converting that deviation score into a special kind of unit, standard deviation units. So the calculation of this, especially when we go to Excel, I think is really quite simple, especially because we have already done the hard part. We have computed the standard deviation. I think what's really kind of amazing about a z-score is that it reflects in a single number measures of both central tendency and variability. So that really deserves a big wow. That single score gives me a lot of information. So here's our old friend, the normal distribution, and we have the very familiar bell-shaped curve, very symmetrical. And as you know from our last presentation, we have, of course, the mean at the center, and then we have these equidistant bands going left and right from the mean in standard deviation units. So they're equidistant, and again, you go to the right or left, 34.1% of the total of the scores. If you go to the right, that's one positive standard deviation unit. If you go to the left, it's -1 standard deviation unit. Well, a z-score is, again, in standard deviation units. So if I said I had a z-score of 1 on a test, the fact that it's positive tells me immediately that it is above the mean, and it tells me just how far above the mean in standard deviation units. So as a little example, let's just say we had a normal distribution of a set of scores. The mean was 75 and the standard deviation was 10. So if I said that one score had a z-score of -1, that would be therefore a raw score of 65. Because again, it would be 10 below the mean of 75. In a similar way, a raw score of 95 would be equivalent to a z-score of 2, because it would be 2 standard deviation units above the mean. Let's use our Girl Scout cookie sales example from the last presentation to help make this all a little clearer. So I have exactly the same data in the table that we had last time, except I've added a fourth column for z-scores. So again, as you know, in the first column we have the raw scores, the boxes of cookies each of the Girl Scouts sold. The second column show the deviation scores, which again is simply the raw score minus the mean. So for example, the first Girl Scout, 28 minus the mean of 10 gives a deviation score of 18. The third column squares the deviation scores, and remember that the lowercase x is a symbol for the deviation score. So the lowercase x is equivalent to the raw score minus the mean. So the z-score is simply going to be the deviation score, which would be 18 in the first Girl Scouts example, divided by the standard deviation of 8.66. So you can see, for example, that third Girl Scout who sold 10 boxes of cookies, which is exactly the mean, would have a z-score of 0, whereas that first Girl Scout who sold the most boxes of cookies has a z-score of 2.08, so just over 2 standard deviation units above the mean. So I hope you can see that the actual computation of a z-score is now actually quite simple, given what we had already accomplished in computing the deviation scores and the standard deviation for this set of data. Also notice that if you sum up all of the z-scores, you're going to get a total of 0, which is, of course, exactly what you get when you sum up all of the deviation scores. And that makes sense because if you think about it, given that the deviation scores are in the numerator for the calculation for a z-score, you're going to have that same mathematical balancing. The same amount is above the mean as is below the mean. So you're going to get 0 as the numerator. Also notice as well that the standard deviation for a set of z-scores is always going to be equal to 1. And that is really consistent with what we just saw a moment ago when we looked at the graph of the normal distribution, given that the z-scores were in standard deviation units, in going 1, 2, 3, 4 in a positive fashion going to the right of the mean, and in a negative fashion going to the left of the mean. So this is a good mathematical check of our work to make sure that we have not done anything incorrectly. We should always do those sorts of checks. So again, the summing up of the z-scores will give me a sum of 0, and I will get a standard deviation of 1. So we've learned that converting raw scores to z-scores allow us to compare scores accurately within the same distribution. But another really interesting and really useful property of z-scores is that they allow us to also compare scores from different distributions in a meaningful way. Let's consider an example. Suppose we give students 2 surveys, one of their attitudes toward reading and another about their attitudes toward mathematics. By converting their raw scores on each of the surveys to z-scores, we can compare any one student's attitudes toward reading and mathematics in a meaningful way. Here I have a table with some data related to these 2 surveys. As you can see, I've extracted out 5 students of all those who were given the survey. You can see that on the attitude toward math, the overall mean was 45.2 and the standard deviation 12.55. On the survey about attitudes toward reading, the mean was 50.73 with a standard deviation of 11.32. So overall, the students surveyed had a more positive attitude toward reading, and they also, their attitude toward mathematics was more varied. So in this table, I've included data just on 5 of the students for us to take a look at. You can see I have a column with their raw scores and also a column with their z-scores. So with the help of z-scores, let's try to make some sense out of the results of these 2 surveys. Let's take a look at student 8, for example. Student 8 scored a 56 on his or her attitude toward mathematics and a slightly higher score, a 57, on the attitude toward reading. So at first glance you might think that this student has a more favorable attitude toward reading than mathematics. However, relative to the total group, when we take a look at the z-scores, we see that the student's attitude toward arithmetic is more positive, 0.86, than his or her attitude toward reading, with a z-score of 0.55. So again, the z-scores can be compared, the raw scores cannot. Of course, there's the exception to this would be when the means and standard deviations of both distributions are identical, then you could make that comparison, but that's obviously very rare. Let's make some other comparisons. For example, student 9, who had the most positive attitude toward arithmetic with a z-score of 1.42, also had a positive attitude toward reading with a z-score of 0.82. On the other hand, the student with the most positive attitude toward reading, student 4, had a z-score of 1.08, but had the most negative attitude toward mathematics with a z-score of negative 2.41. And remember, when you have z-scores, you can, of course, compare 2 scores within a distribution. So, for example, students 3 and 12 had raw scores of 46 and 56, respectively, on attitudes toward reading. Their z-scores show that student 3's attitude to be 0.42 below the mean, and student 12's attitude to be 0.47 above the mean. Let's consider yet another example. I happen to be about 5'11" and I weigh about 185 pounds. So a question I might want to ask myself is, am I taller than I am heavier? Well, that's kind of a weird question. It seems a little bit ridiculous, maybe even somewhat nonsensical, But as it turns out, that actually is a question I can answer. So there I am, by the way, as you can clearly see, outstanding in my field. So by converting my height and weight to z-scores, and then looking up those scores on height and weight distributions of males in the United States, I find out that I am actually taller than 80.1% of the male population, but I weigh more than only 35%. So it does kind of make sense to actually say that I am taller than I am heavier. Well, I think that's enough for now. So I hope this short presentation gave you a good orientation to what a z-score is, how to compute z-scores for each raw score in a data set, and also their use and benefits. You should now be ready to compute some z-scores yourself using Excel. Until next time.